Well, hello and welcome again to our journey into Algebra and Number Theory, and this is the third video in the section on integers. And so we introduce here a very basic result and yet very fundamental in number theory. This is sometimes called the division algorithm. And it says if you start off with two integers a and b, and we'll assume that a is positive, then this essentially says, which something you knew back in primary school, that you can divide b by a, it goes q times, and you get a remainder, and the remainder has to be less than what you're dividing by. Now, although it's a fairly trivial, well-known result, it's interesting that when we look at some more abstract rings, this is not true in general. In fact, the only rings which have one of these division algorithms, the so-called Euclidean rings, are the ones that have this, and there are rings that do not have a meaningful division algorithm in this way, but it happens the set of integers is a Euclidean ring. So, little proof of this. So we consider the set b minus aq, where q is a whole number, an integer, and we let r be the smallest non-negative element of S, so that r is bigger or equal to 0. That is, r then must be b minus some particular multiple of a, and if so r minus a then is b minus a q star minus a, which is b minus a into q star plus 1. Now this is going to have to be smaller than 0 by the minimality of r, and that means that r has to be less than a, because r minus a then is negative. From this we can now prove that every ideal in the integers is a principal ideal. Remember, a principal ideal is one which has one single generator. So no matter what sort of ideal you take in the integers, any ideal in the integers has to be principal. And the proof just follows by using the division algorithm. So we take an ideal I. If it just consists of 0, then we're finished, because it's obviously principal, it's generated by nothing. Otherwise, we choose an element a of smallest positive absolute value. We choose the element of a of smallest positive absolute value, and I claim then that I is just indeed the multiples of this a. It's built up from taking multiples of a. So every multiple of a belongs to I, since I is an ideal. So conversely, I need to show any element of I is a multiple of a. Suppose we take b in the ideal, then we can divide b by this number a that we've constructed. So there exists q and r by the division algorithm, such that b is aq plus r. And r then has to be bigger or equal to 0, but less than what I'm dividing by. So I can rearrange this and write r is b plus minus qa. And of course b is in the ideal, and any multiple of a is in the ideal, and the ideal is closed under addition, so r has to belong to I. And that means that r must be 0, since a is minimal. So if r is less than a, and a is the smallest non-negative element, then r has to be in fact 0. And that will mean back here that b is just equal to aq, and that means that I is just a multiple of a. So just as an example of that, if we take this ideal, that's all the integer linear combinations of 8 and 12, then this, if you write this out, turns out to be just built up by, it's an ideal built from the number 4. So it's a principal ideal with this as a generator. Now you might be tempted to think that all ideals in all rings are principal, but this is not in fact the case. And the following is an example, slightly difficult, but a little example of an ideal which we're going to construct which is not principal. So we take this ring R, which is z root minus 6. So that means it's all things of the form a plus b root minus 6, where a and b are integers. So that's what we mean by this ideal. And it's clearly closed under addition, subtraction and multiplication. You can check that, the zeros in there and so on. So if we take I'm going to take this ideal, which is generated by the number 4, and 2 plus root minus 6. So 2 plus root minus 6 is in this ring, and 4 is in the ring. I put b to be 0, a is 4. I take these two elements and I take the ideal generated by these two. So what that means is then it's all things of the form 4a plus alpha plus 2 plus root minus 6 beta, where alpha and beta are in z root minus 6. Now, we're going to have a contradiction here, so I'm going to suppose that I is a principal ideal, and then show that leads to a contradiction. That means it's just that there is some generator theta, so this ideal is just some any multiple of theta where the multiples come from our ring R. So theta then I can write as a plus b root minus 6 because it's in the set, and with a and b integers. And I note that 4 belongs to the ideal from here, so 4 is in the ideal, so 4 must be some multiple of a plus b root minus 6. This is our theta, which is supposed to be our generator. And similarly 2 plus root minus 6, there it is there, that's in the ideal, so that must be also some multiple R2 of a plus b root minus 6. This is our generator for some R1, R2 in R. Now we want to get rid of the root minus 6. We like to get back to the integers again. We can do that by taking the square. These are complex numbers. I can take the square of the modulus of both sides of each of these two equations. And in that case, if I take this one, for example, I square both sides, I get 16. So the modulus of 4 squared is 16. The modulus of r I write as mod r1 squared, and the modulus of this squared is a squared plus b plus 6b squared. So I'll take the modulus of this thing. And similarly, well, from this then, we can say that a squared plus 6b squared has to go in, be a factor of 16. And similarly, we can take the square of the modulus over here. Now, the square of this modulus is 4 plus 6 is 10. And on this side, I'm going to get modulus of r1 squared times a squared plus 6b squared again. And that says that a squared plus 6b squared goes into 10 as a factor of 10. So we now have a number which is a factor of 16 and as a factor of 10. Well, the only numbers that are factors of both 16 and 10, positive numbers, are going to be 1 and 2. But this has only got factors 1, 2 and 5 doesn't go into 16. Now the only way this equation can be true is b has to be 0, and then I get a squared is 1 or a squared is 2. Well, a squared can't be 2, so that means a squared is 1. So the only integer solutions are a is plus or minus 1 and b is 0. And if I plug that back into what our theta was supposed to be, our theta was supposed to be a plus b root minus 6, so theta in fact is just plus or minus 1. So that means 1 belongs to the ideal, and that means I can write 1 as an integer linear combination of 4 and 2 plus root minus 6. So it's 4 times something, c plus d root minus 6, plus 2 plus root minus 6 times something else, which is e plus f root minus 6. And if we simplify that and equate the numbers in front of the root minus 6, then we end up with 4c plus 2e minus 6f is 1. Well, this doesn't make any, so we equate the integer parts, I should say. So the integer part here is 4c plus 2c minus 6f. That's the bits without the root minus 6, and that has to equal 1 on the other side. Well, this equation is impossible because this left-hand side is even and this number's odd, and so we finally get a contradiction. So we have here an ideal inside this ring, and it's not principal. So So not every ideal is principal, but within the integers, every ideal is principal. Well, you will have noticed by now also that the generator of the ideal Mn in the integers is simply the GCD of M and N. And that means the GCD of M and N then is equal to mx plus ny for some integers x and y. So this is a lovely fact here. This is sometimes known as Bazoo's lemma. I'll write it down formally here. So for example, the ideal generated by 12 and 8 is principal, and its generator is just 4, which is the GCD of those two. And indeed you can write 4 as an obvious integer linear combination of 8 and 12. And that brings us to this very important result, theorem 7, that if M and N are integers, then the ideal generated by M and N is just the ideal generated by the GCD of M and N. And as a consequence of that, we have that the GCD of M and N can be written as an integer linear combination of the numbers M and N that we started with, sometimes called Bazoo's lemma. A little proof of this from theorem 6. We know that M and N has some generator. This is an ideal in the integers, so it's principal, so it's got some generator for some A in the natural numbers. And in the proof of the theorem, we saw that this number A is a factor of M, and this number A is a factor of N. So A is a common factor of M and N. Also, we've seen that A has to be some combination of M and N, so A is equal to mx star plus ny star for some x star, y star and z. And that means any integer divisor of M and N is also going to be a factor of A. And that means that A is the greatest common divisor of M and N. Immediate consequence of this one also is this lovely fact that if P is a prime and P divides the product of two integers, then it must divide one or the other, or possibly both. And the proof, again, this is very simple proof. If P doesn't divide A, then that means the GCD of A and P is 1. So I can apply Bazoo's lemma and write 1 as an integer linear combination of A and P. There it is. Now we've got to get B into the story, so I multiply everything through by B to get to this line. And now P divides this term, and P divides AP by assumption up here, and that means P divides B. So therefore if P divides A, we're finished. If not, then it has to divide B. Now a little corollary that you might like to have a go at proving yourself is that if you've got three integers, if A and X are relatively prime, and if X divides the product A times B, then X divides B. In general, you need this condition. Simply having X divides AB does not imply X divides B, unless X is prime, or unless A and X are relatively prime. Now, we proved earlier that every integer was either 0 plus or minus 1 plus or minus a prime, or plus or minus a product of primes. And this factorisation is unique up to the order of primes. And you can prove this by induction, this result. So, for example, you take 12. There's essentially only one way of factorising it, ignoring order. So no primes other than 2, 2 and 3 can appear in the prime factorisation of 12. This phenomenon is not true in a general ring, which comes as a bit of a surprise. So for example, in the ring Z root 10, we can take the number 6, which is a perfectly good integer in here. You can factor it as 2 times 3, which again are perfectly good integers in this ring, but you can also factor it as 4 plus root 10 times 4 minus root 10, which again are perfectly good numbers in this ring. And these factorizations are incompatible. You can't factorize any of these any further within this ring, it turns out, which is not that hard to show. So none of the 4 factors can be factorized further. In other words, we have 2 essentially different factorizations of 6 in this ring. Now, I'm not going to go into any further detail on this question. Suffice it to say that the problem of unique factorisation is related to the questions of which ideals are principal, in the sense that every principal ideal domain has unique factorisation. Now, you might think about that for a bit, because the integers, for example, we have unique factorisation in the integers, and that is a happy accident as a consequence of the fact that in the integers every ideal is principal. So uniqueness of factorisation in the integers is not as trivial as you might first think. Now, you've probably come across Euclid's algorithm earlier. So we've proven that this ideal m and n is equal to the ideal generated by the GCD. How do we compute it effectively? Well, we simply use the division algorithm over and over again, and that leads us to what's called Euclid's algorithm. Euclid's algorithm is simply repeated application of the division algorithm. So just to do one quick example of this, if we take these two numbers, you divide 81 by 15, it goes 5, remainder 6. Now, the GCD of these two numbers, 15 and 81, equals then the GCD of these two numbers. And so I can repeat the argument now on these two numbers. So 15 is 2b6 plus 3. Again, the GCD of 15 and 6, the same as the GCD of 6 and 3. But when you do the division here, the remainder is 0. So I can immediately write down the GCD of 6 and 3 to be 3. And then backtracking, we get the GCD of these two numbers is equal to 3. Now, working backwards, starting here, we can write 3 as 15 minus 2b6. And what I can do then is I can replace this 6 from this line. I can replace this 6 with 81 minus 5 be 15. And if I expand this out, I get minus 2 lots of 81. I get 30 lots of I get 10 lots of 15, plus one more gives me 11 lots of 15. And so I've written there the GCD of the two numbers as an integer linear combination of the two. So 3 is 15, be 11, minus 2 be 81. Now, this last identity, which relates them, as I mentioned, is called a Bazoo identity. The final T is silent, and the last non-zero remainder we got, which was up here, that's the GCD. You might like to have a go at doing that for 1001 and 72 and express that as an integer linear combination of these two. Now, we're going to see how useful this is in the following chapters, but that is the end of chapter 1 on the integers.